So far when we talk about the evolution of open quantum systems, we use one of the two approaches which are actually equivalent. So we look at it as the evolution of a larger system, a unitary evolution of a larger system, or we looked at the evolution of the system itself in terms of the Kraus operators. But the two pictures are quite equivalent, right? So we can switch between the two. We understand the correspondence between the two. We understand this expression here. So this means take the system, add another system, the environment, do the unitary evolution. So altogether, this can be expressed in terms of this isometry, which is isometric embedding, adding another system and doing a unitary transformation on the joint system. So that's your isometry. So and then of course you do the tracing over the environment and then you look at the system. So that's the final state that you are interested in. We do know now that the partial trace can be expressed in the Kraus representation. So we have already the isometry part, which is in the Kraus representation. So the tracing also gives can be expressed in the Kraus representation. So altogether, the whole evolution can be written in the Kraus representation. So this is fine. So we are quite happy, and we know that this way, looking at the open evolution of an open quantum systems is very satisfying for physicists, because we can see right away that our density operators are mapped into proper legal density operators, in a sense that those maps are certainly positive, so they take positive operators to positive operators, so they're positive, and they also trace preserving. So those conditions here make sure that those maps preserve traces, so they're positive and trace preserving. So if we call a class of maps physically admissible maps that map valid density operators into valid density operators, call this sort of class of operations quantum operations. So we have a set of, let me call it quantum operations or quantum channels. So those quantum operations are certainly represented by positive trace preserving maps. The question is, does it go the other way around? So if we can, in terms of Venn diagrams, I can write a class of positive trace preserving maps, and the question is, are those two sets identical, or are there positive trace preserving maps that are not physically admissible? So is there anything here that we cannot really quite implement, and we don't consider this as a quantum operation? So that's like a more a mathematician's approach to the problem. If you are given a task to guess what are physically admissible operations, what kind of class of maps would you then identify? You would just start thinking this way: okay, it has to be positive, preserve positivity, it has to preserve traces to map density operators into density operators. Is there anything else you would require? Well, it turns out that there is one extra condition. So that let me just illustrate it with a simple example. So I'll just take the transpose. Transpose is a well-defined positive trace preserving map. So given a density operator, we can take the transpose of density operator. So pick up any basis, you have a density matrix, just flip it around the diagonal, right? So it's quite clear that the diagonal elements are not affected, so it's trace preserving, and it's also positive. So it's certainly positive trace preserving operation. Now, is it a legal quantum operation? Can we implement transpose in a lab? Can it be expressed in the Kraus form or this particular form here? Well, the answer is no. Consider what is called a partial transpose. So imagine that we have two subsystems, and let me just draw two lines representing quantum operation, and I feed one subsystem to this channel and I do nothing to this subsystem and let the other subsystem undergoes transpose. So, so this is called a partial transpose, where we just do transpose on one of the two subsystems. So we have a bipartite system, and we just do nothing to one part and take transpose of the other one. Now I'm going to, so you'll see what happened in a moment if I'm just going to take, I'm going to take a maximally entangled state now. So I'm going to take state omega, which is 1 over square root of d, in general in d dimensions, right? D-dimensional state, I. So the density operator is a projector on omega, and as you probably know, it can be written as 1 over d, and I'll have a sum over I and j here, and I have operators I, j, tensor I, and j. So now I do nothing, so I apply identity to all operators pertaining to the first subsystem, and I take transpose. So I apply transpose to all the operators here pertaining to the second subsystem. So that will give me the resulting operator, the resulting matrix, that is the effect of this operation on this maximally entangled state will be a matrix which is 1 over d, sum over I, j, the first part, the first element of the tensor product is not affected, but the second one is, so just we flip it, right? This is a transpose. Now you look at this expression here, and you may just recognize it, that this is sort of this operation will just flip the indices I and j, and the resulting matrix is not a positive matrix. If it is not clear from this form, you just take the simplest case. Always, you know, if not sure about things, go for the simplest example. Take two qubits, put them into the Bell state, maximally entangled state. Write a density matrix at the input. It will be something like this. Well, it will be exactly this matrix. So it's 1 over 2, and this matrix will look like this. So this is your Bell state 0, 0 plus 1, 1, right? So this is your input. You know, 1 qubit goes into this channel, 1 qubit goes into this. So you do nothing to the first qubit, do the transpose, and to the qubit mathematically do the transpose. So what will you get at the output? So because this is a partial transpose, this will only affect the second indices. So if you look at those sub-matrices here, so you'll have a transpose in each block matrix here. So the outcome of this operation is 1 over 2, and you will have this matrix here. So you see, I do the transpose here, so that doesn't affect this matrix. I do the transpose, so this one goes here. I do the transpose in here and transpose here. So this is the resulting matrix. Now look at this matrix here. You can see that the eigenvalues are 1, 1, and whatever are the eigenvalues of this submatrix, and this is 1 and minus 1. So the result is not a positive matrix. So it's quite clear that this extension of transpose, so if we take transpose of the system, one system, that without any reference to anything else, that looks plausible as a physical operation. But as long as we have another reference system and we get the two systems entangled, this partial transpose is not a physically admissible operation. So we require, in fact, that such extensions are always physically admissible, so that not only the operation itself is positive, but any extension of this operation, so tensoring with identity on any other subsystem, should be also a physically admissible operation positive and trace preserving. So this property is called complete positivity. So we require that quantum operations are not only positive, trace preserving, but completely positive and trace preserving. So this class of operation is called completely positive trace preserving. We call it CPTP maps. And as it happens, the completely positive trace preserving map are exactly the maps that can be written in the Kraus representation.